So it's my great pleasure to introduce Bala Krishnamoorthy, who will be speaking to us on linear programming and geometric measure theory.
Thanks, Ian. This is joined with a couple of students. I will acknowledge them as I go. Thanks much for the opportunity to present. And I also want to start by thanking funding from NSF. There are 3 preprints that work is based on. Maybe the easiest way to find them all in one place would be my web page. That has linear programming and geometric measure theory. You might be wondering where the algebraic topology is. Well, maybe linear programming, geometric measure theory, topology. So that's where the connection is. And one slide over what GMT is mostly about. It was developed back in the 1930s, originally to study minimal surface problems, so soap films and bubble conjecture. So by minimal surface, I mean you're given a boundary, a loop, for instance, and you want to find a surface that has that and has the minimal surface. And initial work started in 1930s, but a lot of advances were made in 1960s. And a very interesting problem in this context is that minimal surfaces come, as they say, cheaper by the dozen. So here is a fair example to illustrate the idea. This example was presented by Robert Young in 2013. Your input, remember, you are looking for boundaries. So actually the boundary is made up of an odd number of loops or cycles on Klein bottle. And you find a surface which has that of cycles as a boundary, and we orient them so that the adjacent or nearby cycles go oppositely oriented. So you can consider filling here. By filling, I mean the surface which has that input boundary. You can 5 cylindrical patches on the Klein bottle, which is all of them, but then there will be one loop which will be matched. So you need to use a disk which is in the middle of the Klein bottle. Input is double. So if your input is 2t, so take every loop twice, then actually you can use the surface of the Klein bottle, and that will be a minimal surface. So you use this disk. So in other words, the area of the minimal surface for 2t input is actually smaller than twice the area of the minimal surface for t. And if you take more than 2, of course it keeps going down. There are examples like that. So of course this is perhaps the easiest to understand example, maybe, but examples were given by Young 50 years back. As I know, there is no relationship between these 2 Youngs, but also Frank Morgan and Brian White gave similar examples. They were all, in 4 at least. Of course, you do need to go to R4 to reach this Klein bottle. So the question we are interested in here is, if F is the minimal surface for a curve T, closed curve, makes sense, is 2S also the minimal surface for 2T? And the answer is yes for codimension 1 and 2, not for codimension 3, as this example shows one curve in R4. But in similar questions, but for a more general setting, we ask a similar question for currents. Currents are these objects that are standard objects that are studied in geometric measure theory. For us, I'm not even going to define what currents are. Just think of generalized surfaces with multiplicities and orientation. So one current could be curves maybe sitting in R2, or maybe could be sitting in R3 even. They could be going nearly left and right, oriented, but each piece has an orientation. And in some sense, they are very generalized notions of surfaces and the objects that we are interested in. And notion of mass of a D current is its weighted D volume, or for instance, think of length. For 2D currents, think of area of the entire 2D patch. So the objects that are studied, and we want to distances between such currents. And the couple of choices that you might think of are Hausdorff and Frechet distances. Hausdorff, you can easily come up with examples where it could be problematic. Frechet, of course, distance is quite well studied for one-dimensional currents, at least monotonic curves. There are very efficient algorithms, and very recently there are extending at least some of the ideas to surfaces. But here, as the previous picture shows, you can have the input itself need not be monotonic. It could be a collection of bunch of 1D curves. And so even it's actually, it's not clear to even define a Frechet distance in an unnatural manner. So well, maybe we can take the mass of T1 minus T2. Given two currents T1 and T2, you might think of distance as the mass of T1 minus T2. That also often does not fit into. So if you have two currents like this, essentially following the other but with a wiggle added on, if you take T1 minus T2, all you're doing is reversing it, but you don't, and when you add the mass of this, it's twice the mass of them. So it doesn't actually that they two are actually quite similar to each other. And they are quite sensitive to small changes. For instance, if you move those two curves, which were originally coinciding in this portion by just a little bit, now the mass difference of T1 minus T2 now increased by a lot. Earlier they were cancelling because they are going opposite, but just a little bit, you have a very large difference in mass of T1 minus T2. So you need a definition of distance, and that the flat norm is, it's actually not a norm, it's a semi-norm, but I'll give you some intuition, but here's the formal definition. Given a given T, you for D plus 1 currents S such that you get from sum of T minus boundary of S and S, and for people who are familiar with homology, this is where the T minus boundary of S is where the homology shows up. So you're adding your T into another piece of the same dimension. So T minus boundary of S is the same dimension as T, and S of a one-dimensional higher piece. So you're adding length and area, for instance. So you'd be thinking, well, you're adding apples and oranges. That is the case, but there's a reason why you want to do that. So I'll give a very intuitive idea of what flat norm is. Think a problem you're trying to erase a curve, which is a representation of 1D current, and your operations, and you want to do that at the minimum cost. Is you add another curve, one curve, or another curve of the same dimension, and the cost pay is the length of the curve. So for instance, here the original curve was going from to right as indicated by the arrow. If I add this green curve going the other way, it erases all these parts, and I pay is its length. So now I'm left with this much. I did add these green pieces. But the operation that you can use, you can actually trace boundaries of two regions, and cost you pay is area. So if I trace boundaries of these regions in the correct directionality or orientation, I cancel these loops and I have erased the entire curve. And the sum is the minimum such total cost over of length and area over all such possible erasing operations. Intuitive notion of what flat norm measures. An example illustrating why this is actually a very natural or a good distance. So if you have two currents, you can naturally define a distance between them as the flat norm of P minus Q. Remember, this is not the mass of P minus Q. This is the norm of P minus Q. A simple example to illustrate that. A circle and oriented N1, which is inscribed in the unit circle, both oriented clockwise. I want to measure the distance between them. So as N becomes larger and larger, the N1 essentially comes closer and closer to the circle itself. So you the measure of distance you prescribe also go to 0 as N becomes large. So if I take the mass of T minus Tn, all of Tn here. So now T minus Tn, this by itself is a one current or one curve here. And that norm would just be the area, measure the area between those curves, which I've shaded here in red. And it's not to see that go to 0 as I increase n, because the Tn gets closer and closer to the circle. But mass will to 4 pi. Well, 2 pi for the circle, and the n one also will have a length tending to pi. So you add up and you get 4 pi. So indeed, the form is a natural distance. In this example illustrates that setup. What we do is ask these questions for integral current. Again, they are oriented rectifiable sets with integer multiplicities, finite mass, boundary has also the same properties. Write down mathematically what they are duals to forms and whatnot, but for our purposes, just think integral currents as nice class of currents, nice in big quotes, but they are broad enough to represent anything physically realizable. So especially if you are thinking about applications, this is the class of currents that you want to study. And this question of when is the flat norm decomposition of an integral current also integral? Maybe a simple derivation would be, you could, for instance, represent for writing recognition, you represent each letter or each scribe as a current, one current, and you might think of measure distance between two writings by measuring the flat norm between. And to then ask, well, when are two scripts, when they the same word, for instance. So when their flat norm is small. But then you want to, when you are thinking about applications like that, you want the resulting decompositions to class. When you can say things. So we're always interested in this question of, okay, this is the class of currents we are studying. I want to look for currents in the same class with good properties, but I also make sure that the way in which I'm trying to construct these other currents or look for these other currents will put me in the same class. So the question, when is the flat norm decomposition of an integral current also integral? So the Klein bottle sort of examples. We don't the cheaper by dozen kind of so this is quite old problem. It was actually one of the problems considered by Fred Armgren, who is considered one of the founders of geometric measure theory. It's actually, he didn't publish anything, but this was in a paper written by Brian White, who was one of Armgren's students, and the paper written in the issue in honor of Armgren after he died in '97. So he said that Armgren considered this problem. If 2 is a sequence of integral flat chains, same thing as currents, integral currents, the converge integral flat topology must Ti also converge. So it's a kind of question as the Klein bottle example, but now we are talking about flat norm rather than area minimizing surfaces. And White, to quote White from this paper in '98, Arm used everyone in his arsenal, including his enormous M-2 regularity paper. And I'm not an expert in geometric measure theory, but many of the papers and the books, even the Bible by Federer, it's very, they use very techniques, very heavy tools. And as we know, this problem is still open, and no results are known even for 2 dimensions. So that we can, and we took a very different approach using linear programming and algebraic topology. And here we have what we were able to show for this question: when integral in equal to integral out, it's infinite simplicial setting. So you take discretization, and if you assume things are finite, then it is true for codimension 1 or weak chains in a D+1 complex. It follows from some work that we published in 2013. Well, these, by the way, are in an archive paper which we put on last year. It's under review now. And we used linear programming. That's where the connection comes in. Simplicial setting. What we have done now is we have developed the analysis framework to take it to the continuous setting. Turned out when we started thinking about it, well, how hard can it be? You have the result being for a simplicial complex, should to take finer and finer subdivisions or something and take that and get it. Turns out it's not as trivial as we thought. and we don't have a complete answer either. So the result holds, as in d integral in is integral out for d currents in RD plus 1. By the triangulation result holds, we think it's true, but we have the proof yet. But we have the proof for the triangulation result in 2D, and so no integral in is equal to integral out at 2D. So that's all complete price, but still the framework we think is valid. So in the first part of my talk, I want to kind of give a flavor of things or how we actually ended up with these results. Let me first introduce the idea of flat norm in the SIMPLICIAL setting. So we are thinking about decomposing an input current into the same dimension and the boundary of another piece of one higher. And initial setting, well, we model currents as chains on a SIMPLICIAL complex over by default homology, and everything is overlaid by default for us. And T minus boundary of S as X, and then all doing here is we are looking for X that is homologous to T, the input chain, and we X such that some norm of X as well as S, which defines the homology, is minimized. Since X and T are homologous. So for instance, here if I take T as of these 4 edges, showing down this complex made up of 3 triangles, if I end up all the 3 triangles to define homology between T and X, here X is a small length chain. Norm, when I measure how small it is, not only my include X, but also some notion of areas of all these 3 triangles. So it's optimal homologous chain problem. Given one chain, you want to find another chain that's homologous, which means some weights. Main here is I'm not just minimizing the length X, but also sum of length of X and the area of the one-dimensional chain to define the homology. So to write this down as an optimization problem fashion, the constraint here is just the usual homology constraints. I want X and T to be homologous. So T X is just boundary of one-dimensional higher. I want vectors to be integral. I want to define everything by default over integers. And I'm trying to minimize the weighted sum of the output rather of the same dimension as well as the quote-unquote of one-dimensional higher chain, for instance. So in the edge triangle case, you can think of WA as the length of each edge and V is the area of each triangle. And the others here are because they ignore orientation. So whether you have an edge going forward or backward, you still incur the length of the edge. Similarly, whether you're triangle oriented clockwise or counterclockwise, you still incur the area. So this is not a linear optimization problem, integer constraints, but it turns out these two absolute value terms are linear, and you can easily linearize them. This is a technique that you in an undergraduate linear optimization class, I absolute value term in the objective function, assuming of course weights W, Vj are non-negative, which is a real assumption to make. The length and the of triangles can be taken as non-negative. I'm trying to represent an absolute by the sum of its positive part and negative part. So think, let's say, minus 3. And write minus 3 as the difference of 2 non-negative numbers. So you can say it as like 2 minus 5 or 10, 13 or 26, 20, 19, or write it as 0 minus 3. You want to write it as the difference of 2 non-negative numbers such that the sum of those 2 numbers is small. So that's the minimum is xi plus the positive part and xi minus the negative part. So if you impose that additional restriction that you sum of the 2 parts to be small, then you would just pick 0 and 3. And so 3 is the absolute value. Set technique, I still have the integer restriction, which is what makes this problem by structure. You lose the convexity. So an integer linear program, which by default is called integer program, the first we'll think of is, well, let's throw away the bad restriction, which is the integrality restriction. Then we get something convex, so things are nicer. So you get so here, two-slide introduction to linear programming.
Bala, can I interrupt you?
Sure.
Can we go to the last slide?
Yeah.
So I'm a little confused. So you use kind of a geometric view, which I was sticking to, but I'm in trouble. That the xi's are the edges, or the simplices more generally, and the and absolute value of xi is an unoriented simplex, and xi is an oriented simplex.
Sure.
Now, in the multi-break setting that you write on the equations, you have x being an integer.
Mm-hmm.
So can you help me kind of go from the geometric view to the...
Yeah, it's a integer chain, right? So you have to the picture here. So you can represent your input t as like 1, 2, 3, 4, 5, 6, 7 edges. So you have 7 vector, which is an integer. And here for t, I'll have 1, 1, minus 1 as the values for 4 of those entries and zeros for the other entries. So that vector, right? So I'm writing t as a 7 vector with integer values. If 2 copy t, then I'll just multiply those entries by 2, for instance. And for is another 7 vector which has all zeros except one entry for this edge, which will be a plus 1. So I can think of writing the as a 3 vector here because there are 3 triangles. So this is straightforward linear equation, linear algebra. But that
was helpful. And
okay. Any more?
Now I'm just trying to look at this again. Okay, so the now a vector. It's a member of the free building group on the on the simplices and all right, very helpful.
Okay, so slide intro to optimization or linear programming and integer programming. In optimization in your first calculus classes, well, find the minimum of a function in one table where over an interval a to b, let's say. So you take you find equal points. First derivative is 0, second derivative has to be strictly positive. As your instructor would have told you, you also have to be careful check the endpoint. So in this case, for instance, the min should be at one of the endpoints and not at the critical point. So here it happens to be a local min. Optimize calculus, but if you know the function you are trying to optimize is linear, then you have to take the derivatives and so on. You just need to check the endpoints, because if gx is linear, well, the minimum is at a, maximum is at b. You only need to check the endpoints. So what else is it extends or it takes this easy linear case to higher dimensions. So you still only need to check the endpoints applied in higher dimensions. There are of course some that I need to make, but in general, yeah, you still can just check the endpoints and you're good, because you're trying to, for instance, maximize a linear function x1 plus x2 subject to budget constraints. So instead of the interval, you get a corner region like this. In this case, the endpoints correspond to corner points, and here's your optimal solution. Programming on top of the settings demand or ask for integer optimal solutions. First instinct anyone would be, well, let's just ignore that integer restriction. Now you no longer have convexity, for instance. You're only to the lattice point, so things are not as nice. So maybe you say, let's ignore that and just solve the linear program, which is nice, and then round. So even this example illustrates that the rounding need not go all the time. So the optimization here is 1.8 to 2.1. I could input different ways to any of these 4 points. But which I round, I am not in the feasible region. I go inside this shaded region. The shaded region is a set of points which satisfy all the constraints. So simple may not work, but there are subclasses of problems where you can, as in, you can ignore the integer restrictions and still you're guaranteed to get integer solutions, and properties are still, all properties still hold. And then the concept of total unimodularity comes in. Standard integer programming problem where you're minimizing a linear function subject to a bunch of linear equations and reality restrictions. You want integer solution. So algebra applied multiple times in some sense. But now if you ignore that integer restriction, you get the linear program. The result which says you can always solve the integer program by ignoring the integer restrictions if and only this constraint matrix A is totally unimodular. Here I am assuming it's integer, otherwise things don't make sense. And be integer, if A is totally unimodular, then you can always solve. Always means for every objective function. That's the case. Well, what is total unimodularity? I made TU if every higher subdeterminant is -1, 0, or 1. So think of the typical Kramer's rule. So if a basis submatrix, then it will be non-singular, so it will be -1 or 1. So you're solving Ax equal to B, you are guaranteed to get integer solutions when B is integral. In other words, in the picture that I have shown here, if the matrix here is totally unimodular, then every corner point is guaranteed to have integer coordinates. So ignore the integrality restriction, just solve the linear program. Because the optimal solutions are guaranteed to exist at all points, you are guaranteed to get integer solutions. An example of a modular matrix is node arc incidence matrix of a directed graph. And that's why, for instance, several classes of network optimization problems like shortest path or maximum flow or min cost flow, they're all optimization problems. You can just solve them as linear programs and get integer solutions. We use this result in our integral out question for the currents. In the thing, it turns out you can pick a linear program for the simplicial flat norm. So that this is not in the Ax equal to B form, but after you move all the variable terms to the left, and it turns out that the constraint matrix of this P is totally unimodular if and only if the boundary matrix is totally unimodular. And so there are operations which preserve total modularity. For instance, you can scale a row or a column by a -1, or you can add a singleton row or a column, and so on. It turns out you can construct the constraints of this problem from the boundary matrix using a bunch of those operations. So if and only if the boundary matrix is TU, the constraint matrix is TU, so things are nice. So next natural question will be, when is the boundary matrix of a complex TU? Well, the characterization earlier working with Tamal and Anil Hirani. So we have more general characterization, but in particular in this instance, if you take a +1 boundary matrix of a complex which is sitting in RD +1, is guaranteed to be totally unimodular. So take, for instance, tetra, so complex in R3, and tetrahedra triangle relations, you're sure you have a totally unimodular matrix, and so things are nice. So that we get this affirmative answer. Integral in is integral out for codimension 1 simplicial currents. That's in the finite setting. So it's a difference of posing the problem in the simplicial setting and noticing that boundary matrix is unimodular in codimension. Now, of course, next question would be, can we extend this to the continuous setting? But before this totality connection, there's actually a nice, before that point, the father of algebraic topology, he was talking about results very similar flavor to total unimodularity in 1999. A book, the English translation of his papers came out in 2010, and after our results of definition of unimodularity of simplicial complex boundary matrices, I'm looking at his work, and he defines when there is torsion or not in a simplicial complex in the homology group. So the boundary, he didn't call it boundary matrix, but he talked essentially boundary matrices, and he said this of some matrix cannot be in -1, 0, or 1 for there to be no torsion. So he was already talking about such, although he didn't call it total unimodularity. Total unimodularity as a term came into vogue in the 1950s and 60s when people started studying linear and integer programming. But point was well ahead of his time. But now let's come back to our question. So our question is, okay, so we have integral in equal to integral out for the finite simplicial set. Can we use to get analogous continuous? How would we go about doing that? We can take simplicial approximations of the input chain and sum out the limit of the simplicial complexes and the decompositions, and to get a continuous result. How it turns out, it's not straightforward. There is several issues you have to circumvent, but here's one that I can illustrate quite easily. The simplicial flat norm need not converge to the continuous flat norm, even if norm distance between the simplicial and the continuous current goes to 0. So here's a very simple example. So I am with my input current is this B. Length is fixed, and a simplicial approximation to that, I have two equilateral triangles with appropriate number of points added in the middle. So in this case, K2 has just 4 equilateral triangles. And the upper polygonal chain a simplicial approximation to the straight line. P2 is there. In general, I have Pn. So the circle and n-gon inscribed example. So this flat norm distance between T and Pn, that's 0 because it's just the area of this top half of the triangles, and that finer and finer number of angles that goes to 0 and goes to infinity. But the flat of the top curve is 2 over root 3 times the flat norm of the straight curve, which in case will just be the length. Right? The flat norm of T is just the length of AB, line segment AB, which we are keeping fixed. So we can make finer and finer approximations, but you would still get this 2 over root 3, which is just the ratio of the length is hypotenuse to the altitude here, or base, whichever way you want to think about it. So the flat norm does not converge to the continuous flat. The simplicial flat norm F with the simplicial complex K. So we have to use more heavy techniques, some more intelligent techniques. Here is some of the things that we the polyhedral approximation. So remember, we have the result in a discrete setting or simplicial setting. We think about the continuous setting. So we take the continuous input and push it onto some sort of discrete version and then talk about it. This notion of polyhedral approximation, the standard results in Federer's book, is for normal currents, which are a more general class of currents than integral currents, but for our purpose, integral is enough. So I am the input continuous current T by a polyhedral chain or polyhedral current P. It need be simplicial. It's just, so if you have a continuous curve, I am approximating it by a bunch of pieces of segments, for instance, unit segments, but they're simplicial. So they could intersect in base as far as simplicial complex are concerned. But Martian terms here, to highlight that, so the P is at mass of T plus the additive. So the error is additive in this case. So if we take finer and finer approximation, the error actually goes to 0. The flat distance also 0, as you would expect, but the expansion also goes to 0. And on that, the previous example, not only do we want the flat norm distance to go to 0, but we also want the things not to explode when we push things onto a simplicial complex. But P need to be simplicial. So we want something like this in the simple setting. So that's where we have a simplicial deformation theorem. So this original version we have our 2013 paper. So taking a continuous current and deform it into still currents on a simplicial complex K. Of terms here, but it's bounds. I have mass expansion of P and the boundary and the flat norm distance between the continuous version and the simplicial, in this case a chain. One here is that it's no longer the expansion is no longer just additive. There are these multiplicative factors, C1 times mass of T, and C1, 2, and C3 can be larger than 1. The delta here does go to 0 as we make the simplicial complex finer and finer. So we want clarity simplicial, so but that means we can get a higher blow up in the error of approximation. So if you have an input continuous current and you take a very coarse simplicial complex, I can put this on to this simplicial chain to approximate it. But if you take finer and finer meshes or simplicial complexes, I get a much better approximation. How well rounded these simplices are. Exact how the expansion depends on the qualities, all in how we define the C1, C2, and C3. But anyway, at least that norm does go to 0 as we take finer and finer. We want to be something like the previous case where the mass expansion is additive. So we want to do that. So just simplicial deformation won't get us where we want to go. So with the polyhedral approximation, and then of course the integral out we have in the simplicial set. So we have to do simplicial setting via the polyhedral approximation. So in recent work we have a more general version of the simplicial deformation. It's only for one current, but we have a similar way we can take a bunch of D1s and another bunch of D plus 1 currents and push them all simultaneously to a simplicial complex with similar bounds. So pushing with controlled in a controlled nature. So here how we go and jumps that we face just before you. So I'm starting with a continuous current. I want to get a flat norm decomposition in the X and boundary of S. My question is, if T is integral, can I X and S also integral? Okay. I know it is true in the simplicial set. So first I take a polyhedral version. I approximate T using the approximation theorem. I also consider approximations of X and S in the notion. So call it X delta and S delta. So that P delta and X delta and S delta together, they to each other maybe, but at least one thing we can say for sure is the difference, even if they are not the same, their difference is probably small because both are polyhedral approximations. So making the delta small, we can put differences to small. But now is where we have to push all these things, P delta, X delta, S delta, the whole set onto the simplicial complex, so that we can use the integrality result in the simplicial set. When the crucial step comes in, we have to find one complex which triangulates all these inputs. So a bunch of polyhedral pieces, and to push them all and subdivide a simplicial complex containing all of them so that they all are chains in that simplicial complex. And we do that with controlled mass expansion. Not the flat norm distance is fine, but we also want to control the mass expansion. Okay. Some details in there. And when we have that K delta, assuming we can find that simplicial complex, then we can argue that as delta goes to 0, the flat norm converge. The simplicial flat norm approximates the continuous flat norm with the error going to 0. And then we have the result most because is a simple chain. So it's an integral decomposition because we're looking in codimension 1. And use theorem result, we can view that T should have an integer decomposition. So think there. But the catch is, well, how do you find this nice simplicial complex? At this have a conjecture that we can get we can push the bad parts into corners of the simplicial complex and keep simplicial complex nice. And that's all we are claiming in this conjecture, that we can get enough complex so the bad parts are pushed into corners of small mass. And we do have the result, we do have the conjecture proved in the T case using what terminator triangulation algorithm by Schuchek. We don't in higher dimensions, but we think it should hold true. So our conjecture holds, we do have integral and equal to integral out in dimension 1. So details, they are there in the paper, but the simplicial result in the finite case, and then carefully pushing the continuous input on simplicial complexes, we can get the corresponding result in the continuous. So, kind of end first part with open questions related to this position result. True for any dimension. So we know for sure the result is true in 2 dimensions. But for what about other dimensions? Our framework works in any dimension, assuming this conjecture holds. We can prove that conjecture, then we have the result in higher dimensions. Codimension 1. What about 2? Remember, in the area minimizing surface case, the result both in codimension 1 and in codimension 2, excuse me. So in codimension 3. Dimension 2, we don't know. We don't have the simplicial result either, even in the finite setting. Not complexes, but in computation, in practice, we have observed integrality for free, so to speak, in cases. But at least we have some extreme cases where it's guaranteed not to work. But there is some way in which maybe if you assume a metric space, you can improve it. So the length of the edges in the simplicial complex, areas of the triangles, satisfaction of a triangle inequality in this one. So we don't know. I'll stop here briefly. If you have any questions about the first part, maybe I'll take now, because in the maybe 5 more minutes, I'll just flash through the next part. This part now.
I had a quick question, Bala.
Sure.
So the question was, you outlined this nice framework where you use some of the polyhedral results to go from the continuous setting to the polyhedral to the simplicial setting.
Yeah.
And my question is, before you gave us that overview, you showed that not all simplicial approximations are good. You gave this equilateral triangle example.
Yeah.
So is one of the main ideas that going through the polyhedral setting as an intermediate step, you're finding better simplicial approximations? Is that a fair simplification?
You could think way. The main reason for using the polyhedral approximation in between is the errors in the polyhedral approximation are additive, so it is less than mt plus delta. While if you push directly to simplicial, it is multiplicative.
I see.
So if you can get the integrality result for polyhedral approximations, then we are done. But of course, we don't have integrality results for polyhedral in this whole same setting in the polyhedral approximation. We have integrality result only in the simplicial case. So you want to use the polyhedral result to keep the error terms from crit to high first, and then we want to carefully push it to simplicial complex setting.
Yeah. Thanks.
Okay.
Bala,
Go ahead. Sure.
So this setting, this flat norm is a definition, but it seems to be hopeless to actually compute in practice. Is that right? And I think
so we can compute the flat norm in the simplicial setting in codimension 1.
Okay. The question is that, I mean, it seems that the simplicial one might be hopeful that you have algorithms for computing it. So could you tell us?
Well, the simplicial one in codimension 1 is actually, you can solve it as a linear program. right? So when matrix is totally unimodular, so this is the simplicial flat norm, this one. Integral in, integral out, but you can actually solve the linear program relaxation and you will get the simplicial flat norm. You can compute simplicial flat norm in polynomial time.
Great. So I guess part of this program is to give a computational approach to
Also,
things in the continuous setting.
yes. It not only, so that's where we started in our 2013 paper. We said, oh, here's a way to compute it and have also a way to take any continuous current, form it into a simplicial setting so we can compute it afterwards. But we're saying not only can we compute, but we can actually prove some results from the simple setting actually, because the simplicial setting has some nice structure also.
Thanks.
Okay. In the a few minutes, I want to give a hopefully applied application of this whole framework of currents and flat norm. I'm going of average of shapes. This we hope to have an archive preprint up in the next 2 or 3 weeks. So if you have a bunch of numbers, the average of them is fairly well studied. Everybody knows. So you can think of mean, which minimizes the sum of squares, which minus or sum of the squared deviations. Rather, you find median, which minimizes the sum of absolute deviation or absolute value of deviation. One good property that the median has over the mean is that it's less sensitive to outliers. And this is number, so one dimension. You extend this to higher dimension. So let's kind of view the median line of average because of its good property that it's less sensitive to outliers. This notion of geometric median of a bunch of points in RD, which minimizes the sum of Euclidean distances, not that, but just the sum of distances. So can we talk about medians of general shapes? And talking about this after I introduce the whole machinery of currents, I am talking about can we about medians or averages of shapes that are represented as integral currents. So I'm assuming anything except that they have dimensionality the same. So here, for instance, I have 4 of one-dimensional curves. They may not be monotonic, and they be multiple pieces. One of them might be a loop, and so on. So how do we define averages of such shapes? Of course, shapes is not a new problem. There's a huge body of literature on it. In fact, here's a book on shape and shape theory by Kendall, Barden, Carney, and Lee. For instance, study inside extensive nature, rather the fresh mean. But a common theme of most of these definitions of mean is that they first take the shapes and put two points in some high dimensional space. The space could be just a metric space somehow in some settings, but it could be hyperbolic and it could be quite crazy. The first thing they do is take all the shapes, add them to points in higher dimensions. And so you can just compute the usual averages of points in higher dimensions. Here is, can we actually talk about compute these averages in the space as the input shapes? No good way to map them to such higher dimensional spaces. So, but I'm interested in, otherwise, in generally, can we define and compute medians or averages of shapes in the space of the input shapes themselves? What we've done is we represent the shapes as integral currents or currents in general. Some of the definitions hold for more currents, but in terms of properties that we have proved it for integral currents. And then the actual definition of median shape is the one that minimizes the sum of the flat distances in the candidate and each input current. So argmin sum of flat norm distance between T and Ti. And that when you take the flat norm distance between T and Ti, you are talking about flat T minus Ti, and you are talking about T minus Ti being decomposed into P's of the same dimension and the boundary of one-dimensional higher P's. We pose this question, and for some restricted cases, we could prove existence, regularity, and lots of other nice properties of the median shape in the current setting. But on the side, we pose the same problem in the simplicial setting. So now you have k chains of the same dimension in a simplicial complex. We want to find another chain of the same dimension which minimizes in codes the sum of all these lengths and areas of the decompositions, all actually homology equations. Essentially, T minus Ti homologous essentially. Well, directly, T minus Ti is not just boundary of Si, but it could be another P of the same dimension and the boundary of a higher dimension. So we can try did for the some case we can pose this as a linear program. It turns out that we can throw away the integer restrictions necessarily, but if we do throw away and we are getting integer solutions. So I want to show examples, illustrations of relations. So here we are considering T1 curves in three. Actually, this is a solid ball, so not a three sphere, but a three ball. Are curve sort of coming at 120 degrees and meeting at the north and south pole with some ice thrown in, and we compute median as the north-south diametrical pole length and views. And of this is on a tetrahedral mesh. I am not showing the mesh. The of this approach is that we can also study more general medians, or what we call weighted medians, where I in this weight alpha I in front of the flat norm dishes for T and Ti, and all the alpha i's are non-negative and they sum up to 1. So by changing the alpha i's, I can kind of try entire space median. So in this case, I have actually on a sphere, not on a ball. So I'm not going to get the top to north pole to south pole straight line here, but is 1 for the first curve. I minus just the same as that first curve. By varying the alpha 1 and alpha 2, alpha 2 is 1 and alpha 1 is 0, I go to the other extreme, but a bunch of curves in the middle. And because I'm doing this on a 2 sphere, so generally in the entire space, I can do it on a subspace. I get curves in the middle also. Some more results soon. Here are a couple of questions even related to that. As I said, we don't still works that we solve the linear program and we are getting integer solutions for free, because sure the constraint matrix is not totally modular, but since that we have tried, we are getting integer solutions. So maybe something deeper there that seems to work. And now from the computational point of view, we have defined this nice shape, but we are still solving large linear programs. Maybe more efficient algorithms to find these median shapes so that we can apply them in practice more. So yeah, I stop there. Thank you. If you have more questions, feel free.
Maybe I'll start with a question. So, median of congruence, and I talk about the continuous setting or the simplicial setting.
Sure.
Okay, all right. You've proved existence. Okay, so that was one thing I wasn't sure if you had. What about uniqueness?
Oh, that's a question that we faced right at the beginning. For instance, consider two curves, the upper envelope and lower envelope of a circle, and going from the left endpoint to the right endpoint in the middle, a median according to this definition. And even if you take a mean where we square the flat distance, they're non-unique. But we add a regularity term, so instead of that, I'll say minimize the sum of flat distances and also the mass of T. So I don't want it to wiggle around too much. I want some starts at the left end point and goes to the right end point, but smallest mass, they'll get the straight line in. So all that is a mass regularized median, and we have properties proved for that also. That is actually unique. In meshes, we can prove that that is unique.
And what continuity? So for you have these alphas that you vary.
Yes.
And at least in one of your slides, you kind of gave the impression that this the line would kind of move from one end to the other.
Yes.
Now.
Okay. How smoothly does the black line move from the left to the right depends on how fine the mesh is. So we took a triangulation of the two sphere and we are doing the computations. And we varied alpha 1 and alpha 2, but we did not get meanings in the middle. So there seemed to be a jump, like it will from this point and it's like 0.51 and 0.49, but make it 0.5, it might jump a little. Then when we make 0.4 and 0.6, it might go all the way, much closer to the other side. So that I think is well, two things. One is, of course, how fine the mesh is. So in continuous setting, we can actually prove for the mean, if I actually take alpha times f squared, then we know that it's continuous. Varying as alphas vary from 100 to 001, all of the unit cube, you can actually continuously sample the entire space of medians. But for the median, if you are only adding the sum, we don't know. We are not sure. And even in the computation, we see that it seems to jump discretely. Because computing the mean flat shape is actually harder because of the square term. Because of the square, it's no longer just a linear program. That's the reason why we studied medians.
This example on the sphere, you take the average of the green and the red curve, or maybe a weighted average. So if you're in your little picture, the black curve is maybe pointing towards me, in front of me. Will it somehow flip around and be on the other side of the sphere, the back end of the sphere?
Yeah, it can be.
Is this an example where you don't have uniqueness then, because you could be either on the front or the back half of the sphere?
Yes. Yes, both are valid solutions because there are two ways in which you can get the same length also. Even when you mass regularize, you can this half curve could be the same length as the one that goes behind. Yes.
Right.
Any more questions? All right, let's thank Bala again. So thanks a lot. Thanks for the great.